Alright, can I be heard? Okay. Oh, this is gonna be a problem. Okay, does it work from here? Alright. Just checking that everything works, I guess. Time to start reading. Okay. Testing, 1, 2, 3. Okay. Time to go then. This text is intended for a 1 or 2 semester undergraduate course in abstract algebra. Traditionally, these courses have covered the theoretical aspects of groups, rings, and fields. However, with the development of computing in the last several decades, applications that involved abstract algebra and discrete mathematics have become increasingly important, and many science, engineering, and computer science students are now electing to minor in mathematics. Though theory still occupies a central role in the subject of abstract algebra, and no student should go through such a course without a good notion of what a proof is, the importance of applications such as coding theory and cryptography have grown significantly. Until recently, most abstract algebra texts included few, if any, applications. However, one of the major problems in teaching an abstract algebra course is that for many students it is their first encounter with an environment that requires them to do rigorous proofs. Such students often find it hard to see the use of learning to prove theorems and propositions. Applied examples help the instructor provide motivation. This text contains more material than can possibly be covered in a single semester. Certainly, there is adequate material for a 2-semester course, and perhaps more. However, for a 1-semester course, it would be quite easy to omit selected chapters and still have a useful text. The order of presentations of topics is standard: groups, then rings, and finally fields. Emphasis can be placed either on theory or on applications. A typical 1-semester course might cover groups and rings while briefly touching on field theory, using chapters 1 through 6, 9, 10, 11, the first part of 13, 16, 17, the first part of 18, 20, and 21. Parts of these chapters could be deleted and applications substituted according to the interest of the student and the instructor. A 2-semester course emphasizing theory might cover chapters 1 through 6, 9, 10, 11, 13 through 18, 20, 21, 22, the first part, and 23. On the other hand, if applications are to be emphasized, the course might cover chapters 1 through 14 and 16 through 22. In an applied course, some of the more theoretic results could be assumed or omitted. A chapter dependency chart appears below. A broken line indicates a partial dependency. I'm just gonna post this if this is a VOD or if anyone's here. This is a mess. I'm not gonna try to make sense of it immediately. Alright. Though there are no specific prerequisites for a course in abstract algebra, students who have had other higher level courses in mathematics will generally be more prepared than those who have not, because they will possess a bit more mathematical sophistication. Occasionally, we shall assume some basic linear algebra. That is, we shall take for granted an elementary knowledge of matrices and determinants. It should present no great problem, since most students taking a course in abstract algebra have been introduced to matrices and determinants elsewhere in their career, if they have not already taken a sophomore or junior level course in linear algebra. Exercises sections are the heart of any mathematics text. An exercise set appears at the end of each chapter. The nature of the exercises ranges over several categories. Computational, conceptual, and theoretical problems are included. A section presenting hints and solutions to many of the exercises appear at the end of the text. Often in the solutions, a proof is only sketched, and is up to the student to provide the details. The exercises range in difficulty from easy to very challenging. Many of the more substantial problems require careful thought, so the student should not be discouraged if the solutions is not forthcoming after a few minutes of work. Ideally, students should read the relevant material before attending class. Reading questions have been added to each chapter before the exercises. To prepare for class, students should read the chapter before class and then answer the section's reading questions to prepare for the class. There are additional exercises or computer projects at the end of many chapters. The computer projects usually require a knowledge of programming. All of these exercises and projects are more substantial in nature and allow the exploration of new results in theory. Sage is normally what people would use for open source computations in abstract algebra. We're not going to be using Sage because my computer is on top of a trash can right now. It's not very strong. Don't want to run Sage on it. Okay. Now. So currently, we have the contents and just reading through these in advancement. First, I'm going to read out the acknowledgements and the preface if it is below this, because they want people to be acknowledged. I want to acknowledge them. Then preliminaries, groups, cyclic groups, permutation groups, cosets and Lagrange's theorem, introduction to cryptography, algebraic coding theory, isomorphisms, normal subgroups and factor groups, homomorphisms, matrix groups and symmetries, the structure of groups, group actions, the Silo theorems, rings, polynomials, integral domains, lattices and Boolean algebras, vector spaces, fields, finite fields, and an ending with Galois theory. Now, let's begin. Preliminaries. A certain amount of mathematical maturity is necessary to find and study applications of abstract algebra. A basic knowledge of set theory, mathematical induction, equivalence relations, and matrices is a must. Even more important is the ability to read and understand mathematical proofs. In this chapter, we will outline the background needed for a course in abstract algebra. 1.11. A short note on proofs. Abstract mathematics is different from other sciences. In laboratory sciences, such as chemistry and physics, scientists perform experiments to discover new principles and verify theories. Although mathematics is often motivated by physical experiments or by computer simulations, it is made rigorous through the use of logical arguments. In studying abstract mathematics, we take what is called an axiomatic approach. That is, we take a collection of objects, let's call it S, and assume some rules about their structure. These rules are called axioms. Note here that axioms doesn't just refer to, for those who know, set theoretic axioms. This is more so in an order theoretic way, where the axioms of some structure are literally just the description of what that structure is in full generality. Using the axioms for S, we wish to derive other information about S by using logical arguments. We require that our axioms be consistent. That is, they should not contradict one another. We also demand there not to be too many axioms. If such a system is too restrictive, there will be a few examples, and a few examples only, out of the mathematical structure. A statement in logic or mathematics is an assertion that is either true or false. Considering the following examples: 3 plus 56 minus 13 plus 8 over 2. All cats are black. 2 plus 3 equals 5. 2x equals 6 exactly when x equals 4. If ax squared plus bx plus c equals 0 and a is not equal to 0, then x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And x cubed minus 4x squared plus 5x minus 6. All but the first and last examples are statements and must be either true or false. If you're wondering why we assume them to be true or false, that's actually, I'm just going to be going on a bunch of rants while I'm reading this. That is in itself an assumption. It's called law of excluded middle, and it doesn't necessarily hold to be true, but mathematics is most cleanly done when statements are either true or false. So for a majority of the time, we just assume that all statements are true or false, and we just don't worry about the ones that are not decidable. A mathematical proof is nothing more than a convincing argument about the accuracy of a statement. Such an argument should contain enough detail to convince the audience. For instance, we can see that the statement 2x equals 6 exactly when x equals 4 is false by evaluating 2 times 4, and noting that 6 is not equal to 8, an argument that would satisfy anyone. Of course, audiences may vary widely. Proofs can be addressed to another student, to a professor, or to a reader of a text. If more detail than needed is presented in the proof, then the explanation will be either long-winded or poorly written. If too much detail is omitted, then the proof may not be convincing. Again, it is important to keep the audience in mind. High school students require much more detail than do graduate students. A good rule of thumb is an argument in an introductory abstract algebra course is that it should be written to convince one's peers, whether these peers be other students or other readers of the text. So basically, a way of saying we're not worrying about formal proof, we're just worrying about informal proof. Let us examine different types of statements. A statement could be as simple as 10 divided by 5 equals 2. However, mathematicians are usually interested in more complex statements such as if P, then Q, where P and Q are both statements. If certain statements are known or assumed to be true, we wish to know what we can say about other statements. Here, P is called the hypothesis, and Q is known as the conclusion. Screw what this example is, also just so I can practice using the setup. So, for example, we have the statement P, that the statement will just be like, x is even. Actually, no, I shouldn't put it in set theoretic notation. X is even. And Q is a statement that x divided by 2 is a positive integer, which will be denoted by this. Now, we notice that if x is even, then x equals 2n. So x over 2 equals n in the integers. So we say that P implies Q. I'll just keep that on there for now. also for testing purposes. Let's actually read the example they give. Consider the following statement. If ax squared plus bx plus c equals 0, and a is not equal to 0, then x equals negative b plus or minus the square root of b squared minus 4ac over 2a. The hypothesis is ax squared plus bx plus c equals 0, and a is not equal to 0. The conclusion is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Just going to speed that up because that's a lot. Notice that the statement says nothing about whether or not the hypothesis is true. However, if this entire statement is true, and we can show that ax squared plus bx squared plus c equals 0 with a not equal to 0 is true, then the conclusion must be true. A proof of this statement might simply be a series of equations. Ax squared plus bx plus c equals 0. Then we subtract some c from both sides, divide all that out by a, then we're able to factor it, completing the square as per normal. And then finally end up just doing some simple algebraic manipulations, noting the equivalence of some statements, and we ultimately get x equals negative b plus or minus square root of b squared minus 4ac over 2a. If we can prove a statement true, then that statement is called a proposition. A proposition of major importance is called a theorem. Sometimes, instead of proving a theorem or proposition all at once, we break the proof down into modules. That is, we prove several supporting propositions, which are called lemmas, and use the results of these propositions to prove the main result. If we can prove a proposition or theorem, we will often, with very little effort, be able to derive other related properties called corollaries. Some cautions and suggestions. There are several difficult strategies for proving propositions. In addition to using different methods of proof, students often make some common mistakes when they are first learning how to prove theorems. To aid students who are studying abstract mathematics for the first time, we list here some of the difficulties that they may encounter and some of the strategies of proof available to them. It is a good idea to keep referring back to this list as a reminder. Often techniques of proof will become apparent throughout this chapter and the remainder of this text. No, wait, not often, just the word out there, okay. A theorem cannot be proved by an example. However, the standard way to show that a statement is not a theorem is to provide a counterexample. What that means is that commonly, if we're saying that for all objects of this form, this property is true, to prove that false, well, by definition, we must simply show that there is an object such that that property is false. Quantifiers are important. Words and phrases such as only, for all, for every, and for some possess different meanings. Never assume any hypothesis that is not explicitly stated in the theorem. You cannot take things for granted. Suppose you wish to show that an object exists and is unique. First, show that there is actually such an object. To show that it is unique, assume that there are two such objects, say R and S. Then, show that R equals S. Sometimes, it is easier to prove the contrapositive of a statement. Proving the statement if P then Q is exactly the same as proving the statement if not Q then not P. Although it is usually better to find a direct proof of a theorem, this task can sometimes be difficult. It may be easier to assume that the theorem you are trying to prove is false, and hope that in the course of your argument you are forced to make some statement that cannot possibly be truth. Remember that one of the main objectives of higher mathematics is proving theorems. Theorems are tools that make new and productive applications of mathematics possible. We use examples to give insight into existing theorems and to foster intuitions as to what new theorems might be true. Applications, examples, and proofs are tightly interconnected, much more so than they seem at first appearance. Okay, it looks like stream is still working well, just double checking that. 1.2, sets and equivalence relations. Set theory. A set is a well-defined collection of objects. That's all we're going to need for now. That is, it is defined in such a manner that we can determine for any given object X whether or not X belongs to the set. The objects that belong to a set are called its elements or members. We will denote sets by capital letters, such as A or X. If A is an element of the set A, we write A is an A, with an E in between denoting the A. A set is usually specified either by listing all of its elements inside a pair of braces, or by stating the property that determines whether or not an object X belongs to the set. We might write X is equal to X1, X2, all the way to Xn, or sometimes we may say X sub n, for a set containing elements X sub 1, X sub 2, all the way to X sub n. Or X equals the set of all X, such that X satisfies P, if each X in X satisfies a certain property P. For example, if E is a set of all even positive integers, we can describe E by writing either the set explicitly, E equals 2, 4, 6, on and on, or E equals X, such that X is an even integer and X is greater than 0. We write 2 as an E when we want to say that the number 2 is in the set, and negative 3 is not an E to say that negative 3 is not in the set E. Some of the most important sets that we will consider are the following. N, or you would type this in LaTeX, /mathbbn. N, with N a natural number. Note that in this book, the natural numbers begin at 1. In some books, mainly computer science focused books, you will find natural numbers beginning at 0, since computer scientists are commonly listing things beginning at 0. And /mathbbz equals n. N is an integer, which is listed as a set from braces forward, the negative 1, 0, and 1, 2, on and on. Oh gosh, I'm having a fun time with my internet, it looks like. Okay. /mathbbq equals R. R is a rational number. All rational numbers are written P over Q, with P and Q integers, with specifically Q non-zero. R is then /mathbbr with X for X is a real number. As well for complex numbers, which will be useful at multiple points in this book, /mathbbc for Z. Z is a complex number. We can find various relations between sets, as well as perform operations on sets. A set A is a subset of B, written A subset B or B subset A, if every element of A is also an element of B. Note here that when we're saying that, we aren't necessarily requiring strict equality. Alright, for example, for the set containing 4, 5, 8 is a subset of the set containing 2, 3, 4, 5, 6, 7, 8, and 9. And the natural numbers are a subset of the integers, are a subset of the rational numbers, are a subset of the real numbers, are a subset of the complex numbers. Trivially, every set is a subset of itself. A set B is a proper subset of A if B is a subset of A, but B is not equal to A. If A is then not at all a subset of B, we write A / through the subset B. For example, 4, 7, 9 is not a subset of 2, 4, 5, 8, and 9, since 7 would be required to be in the second set. Two sets are equal, written A equals B, if we can show that A is a subset of B, and B is a subset of A. It is convenient, very convenient, trust us, to have a set with no elements in it. This set is called the empty set, and is denoted by, I will probably read that as either empty set or theta. Note that the empty set is a subset of every set. To construct new sets out of old sets, we can perform certain operations. The union A union B of two sets A and B is defined as A union B is equal to all x such that x is in A or x is in B. The intersection of A and B is defined by A cap B, or A intersection of B, equals x with x is in A and x is in B. For example, here, if A is equal to the set 1, 3, and 5, and B is equal to the set 1, 2, 3, and 9, then A union B is equal to 1, 2, 3, 5, and 9, and A cap B is equal to 1, 3. We can consider the union and the intersection of more than two sets. In this case, we write the big cup from I equals 1 to n of A sub I, which is just the same as A sub 1, union with A sub 2, all the way to union with A sub n. And big cap from I equals 1 to n is of A sub I is equal to A sub 1, cap A sub 2, cap all the way up to cap A sub n. For the union of an intersection, respectively, of the sets A1 all the way to AN. When two sets have no elements in common, then they are said to be disjoint. For example, if E is the set of even integers and O is the set of odd integers, then E and O are disjoint. Two sets A and B are disjoint exactly when A cap B is equal to the empty set. Sometimes we will work within one fixed set U, called the universal set. For any set A as a subset of U, note very clearly that before we start working with this, we call U the universal set. We define the complement of A, denoted by A prime, to be the set A prime equals X, such that X is in U and X is not in A. Notice here, it is meaningless to refer to the complement without specifying a universe beforehand. Especially when we get to topology, that's going to be a very big thing. And generally in set theory, you may understand why this is a reasonable, if you work with set theory, you may understand why this is a reasonable restriction. Sometimes, I read that, shoot, okay. We define the difference of two sets A and B to be A set minus B equals, note that in here, we're assuming A and B to be part of the same universe. A cap B prime equals X such that X is in A and X is not in B. You will also commonly see this written in subtraction notation. Commonly difference notation in undergraduate text means removal, but when you get to topology, it means quotienting under that space. Example 1.1. Let R be the universal set, and suppose that A is a set of real numbers strictly between 0 and non-strictly below 3. And B is equal to the set of real numbers such that 2 is loosely below X and 4 is strictly above X. So, let me write this in notation, which is less painful. A equals 0. B is equal to 2, 4. So we'll have A cap B is equal to the closed interval from 0 to 3. We have A cup B is equal to the open interval 0 to 4. A slash set minus B is equal to the open interval from 0 to 2. and we will commonly write the complement because it's referring to the universe of the real numbers, in this case most likely, as being from negative infinity to 0 inclusive, unioned with 3 to infinity. Now, here we have one of our first propositions. Proposition 1.2. Let A, B, and C be sets. Then A union A is equal to A cap A is equal to A, and A set minus A equals the empty set. 2. A union the empty set equals A, and A cap the empty set equals the empty set. 3. We will later call this associativity. A union B union C equals A union B union C, and A cap B cap C equals A cap B cap C. 4. A union B is equal to B union A, and A cap B equals B cap A. 5. A union B cap C equals A union B cap A union C. 6. A cap B union C equals A cap B union A cap C. Proof. We will prove 1 and 3 and leave the remaining exercises to be proven in the exercises. 1. Observe that A union A is equal to the set of all x such that x is in A or x is in A. Well, obviously, is x is in A, then it's in A. It's literally the same statement. So we can reduce that to the set of all x such that x is in A, which by the definition of what it is the set A. Similarly, we can define x to be x in A and x in A. Well, x is in A only if x is in A, so once more we can make the reduction. And then we get that the set of all x such that x is in A is just A. Also, for A set minus A, we have A cap A prime. So, supposing we had an element A in A cap A prime, then that would imply that A is both in A and not in A, which is impossible. By how we're defining sets, we cannot have an element both be and not be in a set. 3. For sets A, B, and C, A union B union C equals A union the set of all x such that x is in B or x is in C is equal to the set of all x such that x is in A or x is in B or x is in C. Then we can take out that x in C, factor that out to be x such that x is in A or x in B union with the set C, which is just the same as A union B union C. A similar argument proves that A cap B cap C equals A cap B cap C. Theorem 1.3, De Morgan's laws. Let A and B be sets. Then A union B complemented equals A complemented cap B complemented. And 2. A cap B complemented is A cap complemented union B complemented. Proof. 1. If A union B is equal to the empty set, then the theorem must follow immediately, since both A and B are the empty set. Otherwise, we must show that A union B cap is a subset of A cap B cap, or B prime. Why do I keep saying cap? Oh no. And A union B prime is a superset of A cap, A prime cap B prime. First of all, what we're going to do is we're going to show that if x is in A union B prime, it's in A prime cap B prime. So, let x be in A union B prime. Then, x is explicitly not in A or B. So, as it says, x is neither in A nor B, by the definition of the union of sets. By the definition then of a complement, we have that both x is in A prime and x is in B prime. Therefore, x is in A prime cap B prime and we have A union B prime is a subset of A prime cap B prime. To show the reverse inclusion, suppose that X is an A prime cap B prime. Then X is an A prime and X is in B prime, and so X is not in A and X is not in B. Thus, we have X not in A union B because it's in neither, and so X is in A union B complement. Hence, A union B complement is a superset of A prime cap B prime, and so A union B prime is equal to A prime cap B prime. We let the proof of 2, which is just a similar thing for complement, like switching the cups and the caps, as exercise. Example 1.4. Other relations between sets often hold true. For example, A set minus B, cap B set minus A is equal to the empty set. To see that this is true, observe that first, A set minus B, cap B set minus A is equal to A cap B prime, cap B cap A prime. This is just by definition of what we mean by set minus. Then, by our earlier associative law, that we don't have to worry about parentheses functionally when doing caps, we can remove them and just have rearrange the order of the terms to be A cap A prime, cap B prime. Now, A cap A prime is obviously the empty set, since A prime is defined to be the set of all elements that are not in A, and it's likewise for B prime. So we have the empty set cap the empty set, which is just obviously the empty set. Cartesian products and mappings. Given sets A and B, we can define a new set A times B, called the Cartesian product of A and B, as a set of ordered pairs. That is, A times B is equal to the set of all pairs A, B, such that A is in A and B is in B. Example 1.5. If A is equal to X, Y, and B is equal to 1, 2, 3, and C is equal to 0, my apologies, then A times B is the set X1, X2, X3, Y1, Y2, Y3, and A times C is equal to the empty set. It's important to note, because this is very commonly used in proofs involving products to avoid annoying base cases, that we assume that the product of any set with the empty set is again the empty set. We don't provide any special meaning to it. We don't say it's undefined. We just say it is the empty set. We define the Cartesian product then of n sets to be the pair A1 to AN with AI in AI for I equals to 1 to n. You could also think of this, if you so desired. I'm going to clear up a space of this. A1 times A2 times not X, oh no, A to the n. Well, the way we interpret this is first we have A1 times A2 times A3 times blah blah blah, and we evaluate these and then evaluate the 3 and then so and so on. So we can really think of some pair, if we want to get really technical about it, A2 to AN to be A1, A2, A3, on and on. And necessarily, what this means is that if we have two products as in we have the ability to multiply two sets by each other by doing this operation, which is sometimes referred to as currying in the context of functions, we have, I'm going to call them infinity products, which is just arbitrarily large products in this case. Now, subsets of A times B are called relations. We will define a mapping or a function as a subset F of A times B from a set A to a set B to be the special type of relation where each element A in A has a unique element B in B, such that A and B is in F. Note here an important condition, that given A, first of all, there does exist a B, such that f of A is defined in B, right? But besides that, we also have it that it's unique. This is what makes it a function versus just a regular relation. If you go more into, as I'm doing right now, computer science and such, you will see this generalized because sometimes it's not very useful to force the entire domain to be covered. A lot of times we only care that there is at most one output, but for the purposes of this book, we just say that this is how functions are inherently defined. Now, another way of saying this is that for every element in A, f assigns a unique element in B. We usually write f as a function from A to B, or f semicolon A arrow pointing to the right B, or A arrow with a little f above B. Instead of writing down ordered pairs A, B in A times B, we write f of A equals B, or f is A maps to B. The set A is called the domain of f, and f of A, f of capital A, equals set of all f of A with A and A, as A subset of B, is called the range or image of f. We can think of the elements in the domain, in the function's domain, as the input values, and the elements in the function's range as output values. Example 1.6. Suppose A is equal to the set 1, 2, and 3, and B is equal to the set A, B, and C. In figure 1.7, we define relations f and g from A to B. The relation f is a mapping, but g is not, because 1 in A is not assigned to a unique element in B. That is, g of 1 equals A, and g of 1 equals B. So, for example, in the first diagram, we have A as being from the 3 set, and it maps 1 to B, and 2 and 3 to C. And in the second case, we have A maps, well, A is actually not a function, because we have 1 mapping both to A and to B. We don't have a single one it's mapping to. It's not unique in the way that we require functions to be. Now, given a function f of A to B, it is often possible to write a list describing what the function does to a specific element in the domain. However, not all functions can be described in the manner. For example, the function f from R to R that sends each real number to its cube is a mapping that must be described by writing f of x equals x cubed, or f from x to x cubed. You literally do not even have the ability to list down all the real numbers. So like describing a function between them is an impossible task. You must use a rule that gives you a computation to follow. Consider the function f from the rationals to the integers given by f of p over q equals p. We know that 1/2 is equal to 2/4. But is f of 1/2 equal to 1 or 2? This relation cannot be a mapping because it is not well defined. A relation is well defined if each element in the domain is assigned to a unique element in the range. Notice something here. We can define f of p over q to be equal to p, and we can have it be a function. However, what that would mean is that 1/2 is not equal to 2/4. There's some sense of structure on the space that we're mapping from and to, some equivalence of fractions in this case, that we want to be preserved. And we will see this commonly with functions when we eventually get to the channel, like the chapters on homomorphisms and isomorphisms. Many of these functions are defined to preserve something, some equivalence on your space, with two things being equivalent implying that two things being equivalent in a certain construction, implying that they are equal in the output of a function. Off that tangent. If f of A to B is a map, and the image of f is B, i.e. f of A is equal to B, then f is said to be onto, or surjective. In other words, if there exists an A and A for each B and B, such that f of A equals B, then f is onto. A map is 1-to-1 or injective if A1 is not equal to A2, implies f of A1 is not equal to f of A2. Equivalently, a function is called 1-to-1 if f of a1 equals f of a2 implies a1 is equal to a2. A map that is both 1-to-1 and onto is called bijective. Example 1.8. Let f from the integers to q be defined by f of n equals n over 1. Then f is 1-to-1, but n is not onto. Define g from q to z by g of p over q equals p, where p over q is a rational number expressed in its lowest terms with a positive denominator. The function g is onto, but not 1-to-1. In that sense, we're saying that in the sense that g maps two non-equivalent rational numbers to an equivalent integer. Given two functions, we can construct a new function by using the range of the first function as the domain of the second function. Let f from a to b and g from b to c be mappings, and define a new map called the composition of f and g from a to c by g composed with f of x equals g of f of x. So looking at this graph right here, we have the composition function. First, let's see where the composition function sends 1. Well, we see that 1 is sent to b by f, and we see that b is then sent to z by g. So we know that the composition 1 will be sent to z. Similarly, 2 is sent to c and then to x. So 2 is sent to x in the final one. And finally, 3 is sent to a, and a is sent to z. So 3 is sent to a in the final one. Example 1.10. Consider the functions f from a to b and g from b to c that are defined in figure 1.9, or the figure above. The composition of these functions, g composed with f from a to c, is defined in figure 1.9, or this combination of blobs right here. Example 1.11. Let f of x equals x squared and g of x equals 2x plus 5. Then f composed with g of x equals f of g of x equals 2x plus 5 squared, and 4x squared plus 20x plus 25 is the second equality. And g composed with f of x equals g of f of x equals 2x squared plus 5. In general, order makes a difference. That is, in most cases, f composed with g is not equal to g composed with f. In a sense, our normal rules of arithmetic over the real numbers, that a times b equals b times a, can fail over certain, we'll call them later, spaces. Example 1.12. Sometimes it is the case that f composed with g is equal to g composed with f. Let f of x equals x cubed, and g of x equals the cube root of x. Then, f composed with g of x equals f composed with g of x equals f of the cube root of x equals the cube root of x squared equals cube root of x cubed equals x. And g composed with f x is equal to g of f of x equals g of x cubed equals cube root of x cubed equals x. Example 1.13. Given a 2x2 matrix A with entries A, B, and C, D, we can define a map T of A from R squared to R squared by TA of xy equals AX plus BY and CX plus DY. The linear transformation, well, this is just a linear transformation associated with that matrix for x and y in R squared. This is actually matrix multiplication. That is ABCD of xy equals AX plus BY, CX plus DY. Maps from Rn to Rm given by matrices are called linear maps or linear transformations. Example 1.14. Suppose that S is equal to the set 1, 2, and 3. Define a map. We're going to be using the symbol pi to denote functions here. S to S by pi 1 equals 2, pi 2 equals 1, and pi 3 equals 3. This is a bijective map. An alternative way to write pi is 1 with below it pi of 1, 2 with below it pi of 2, and 3 with below it pi of 3. And we can see, right-wise, this is basically the diagrams we've been looking at, but now vertical instead of horizontal. 1 is sent to 2, 2 is sent to 1, and 3 is sent to 3. For any set S, a 1-to-1 and onto mapping pi from S to S is called a permutation of S. Theorem 5.1.15. Oh, excuse me. I need to take a drink of Diet Coke for this. Okay, I'm good. Let f from a to b be a function, g from b to c be a function, and h from c to d be a function. Then, the composition of mappings is associative. That is, h composed with g composed with f is equal to h composed with g composed with f. If f and g are both 1-to-1, then the mapping g composed with f is 1-to-1. If f and g are both onto, then the mapping g composed with f is onto. And if f and g are bijective, then so is g composed with f. Proof. We will prove 1 and 3. Part 2 is left as an exercise. Part 4 follows directly from 2 and 3. 1. We must show that h composed with g composed with f equals h composed with g composed with f. For a in A, we have h composed with g composed with f composed with a, with input a, equals h of g composed with f of a, equals h of g of f of a, equals h composed with g of f of a, equals h composed with g composed with f of a, which is equivalent to showing, because it's equivalent on every input, that the two functions are actually equal in the first place. 3. Assume that f and g are both onto functions. Given c and c, we must show that there exist in A and A, such that g composed with f of A equals g composed with f of A equals c. However, since g is onto, there is an element b in B such that g of b equals c. Similarly, if an A in A such that f of A equals b, accordingly, g composed with f of A equals g of f of A equals g of b equals c. If S is any set, we will use the identity of S, our IDS or ID, to denote the identity mapping from S to itself. Define this map by IDS is simply just equal to S for all S and S. A map G from B to A is an inverse mapping of F from A to B if G composed with F equals ID of A, and F composed with G equals ID of B. In other words, the inverse of a function simply undoes the function. A map is said to be invertible if it has an inverse. We usually write f to the negative 1 for the inverse of f. Note that f to the negative 1 doesn't refer to like 1 over something in this case. It refers strictly to an inverse. Example 1.16. The function f of x equals x cubed has inverse f to the negative 1 of x equals the cube root of x by example 1.12. Example 1.17. The natural logarithm and the exponential function f of x equals log of x and f to the negative 1 of x equals e to the x are inverses of each other, provided that we are careful about choosing domains. Observe that f of f to the negative 1 of x equals f of e to the x equals log of e to the x equals x, and f to the negative 1 of f of x equals f to the negative 1 of log of x equals e to the log of x equals x, whenever composition makes sense. Remember, the logarithm is not defined in a nice way, like below 0. And even if you try to extend it analytically, you run into problems on the complex plane. So you must have a well-defined input in this. Example 1.18. Suppose that, give me a sec, my throat. Example 1.18. Suppose that A is the matrix 3, 1, 5, 2. Then A defines a map from R squared to R squared by TA of x, y equals 3x plus y, 5x plus 2y. We find an inverse of a map TA by simply inverting the matrix. That is, t to the negative 1 of a equals t to the t of a to the negative 1. In this example, a to the negative 1 equals 2, negative 1, negative 5, 3. Hence, the inverse map is given by t to the negative 1a of xy equals 2x minus y, negative 5x plus 3y. It is easy to check that t to the negative 1a composed with ta of xy equals ta composed with ta to the negative 1 xy equals xy. Not every map has an inverse. If we consider the map tb of xy equals 3x 0, given by the matrix 3, 0, 0, 0, then a matrix would have to be of the form t to the negative 1b of xy equals ax plus by plus cx plus dy, and xy equals tb composed with tb to the negative 1xy equals 3ax plus 3by 0 for all x and y. Clearly, this is impossible because y just might not be 0. Example 1.19. Given the permutation 1 goes to 2, 2 goes to 3, 3 goes to 1, on s equals 1, 2, 3, it is easy to see that the permutation defined by pi to the negative 1, 1 goes to 3, 2 goes to 1, 3 goes to 2, is the inverse for pi. In fact, any bijective mapping possesses an inverse, as we will see in the next theorem. Theorem 1.2. A mapping is invertible if and only if it is both 1-to-1 and onto. A quick reminder that this may seem simple, but if you eventually go to study something like category theory, this is something that cannot be taken for granted. This is something, in category theoretic language, that in the category set, an isomorphism or a function is an isomorphism if and only if it is a mono and epimorphism. There's more going on underneath the surface than it might seem with this theorem. Proof. Suppose, first, that f of a to b is invertible with inverse g from b to a. Then g composed with f equals a dA is the identity map. That is, g of f of a equals a. Now, if a1, a2 is an a with f of a1 equals f of a2, then a1 equals g of f of a1 equals g of f of a2 equals a2. Consequently, f is 1-to-1 because we've shown that any equal output functions are equal in the inputs. Now, suppose that b is in b. To show that f is onto, it is necessary to find an a and a such that f of a equals b, but f of g of b with a equals b with g of b even a. Let a equal g of b. Conversely, let f be bijective and let b be in b. Since f is onto, there exists an a and a such that f of a equals b. Because f is 1-to-1, a must be unique. Define g by letting g of b equal a. We have now constructed the inverse of f. Equivalence relations and partitions. A fundamental notion in mathematics is that of equality. We can generalize equality with equivalence relations and equivalence classes. An equivalence relation on a set X is a relation R as a subset of the Cartesian products of X and X, such that, first, X and X is in R for all X and X. Notice, this is a statement of existence. This is saying that our relation has something for every X, no doubt. 2. X is in Y in R implies Y and X is in R symmetry. Note also, this is saying something about a pair that already exists. The first rule is different quantitatively in the sense the second and third rules. The second and third rules tell you how to interact with things that exist. The first tells you that things do exist, which is a very important difference. Third, X and Y and Y and Z is in R implies that X and Z is in R. Now, given an equivalence relation R on a set X, we usually write X sim Y instead of XY in R. If the equivalence relation already has an associated notation such as equivalence, or isomorphism, as we will eventually call it, we will use this notation. Example, let P, Q, and R and S be integers, where Q and S are non-zero. Define P over Q is similar to R over S if PS is equal to QR. Clearly, similarity is reflexive and symmetric. To show that it is also transitive, suppose that P over Q is similar to R over S, and R over S is similar to T over U, with Q, S, and U all non-zero. Then PS equals QR, and RU equals ST. Therefore, PSU is equal to QRU is equal to QST. Since S is not equal to 0, PU is equal to QT. The reason we required that is so that we can divide everything by S, if you notice in the expression. Consequently, P over Q is similar to T over U. Example 1.22. Suppose that f and g are differentiable functions on R. We can define an equivalence relation on such functions by letting f of x similar to g of x if f prime of x is equal to g prime of x. It is clear that similar is both reflexive and symmetric. To demonstrate transitivity, suppose that f of x is similar to g of x and g of x is similar to h of x. From calculus, we know that f of x minus g of x equals e1 and g of x minus h of x equals c2. Excuse me. Where c1 and c2 are both constants. Hence, f of x equals minus h of x, equals f of x minus g of x plus g of x minus h of x equals c1 plus c2. And f prime of x minus h prime of x equals 0. Therefore, f of x is similar to h of x. Oh gosh, okay, give me a second. Example 1.2.3. For x1, y1, and x2, y2 in R2, define x1, y1 is similar to x2, y2 if x1 squared plus y1 squared equals x2 squared plus y2 squared. And it's easy to see by literally just the equivalence already in this definition that similarity is an equivalence relation on R squared. Example 1.24. Let A and B be 2 by 2 matrices with entries in the real numbers. We can define an equivalence relation on the set of 2 by 2 matrices by saying A is similar to B if there exists an invertible matrix P such that PA, P to the negative 1, equals B. For example, if A is equal to 1, 2, negative 1, 1, and B is equal to negative 18, 33, negative 11, 20, then A is similar to B, since PA, P to the negative 1 equals B, where P equals 2, 5, 1, 8. Let I be the 2 by 2 identity matrix, that is, I is equal to 1, 0, 0, 1. Then I to the negative 1 equals I equals A. Therefore, the notion is reflexive. To show symmetry, suppose that A is similar to B. Then there exists an invertible matrix P such that PAP to the negative 1 equals B. So, A equals P to the negative 1 BP equals P to the negative 1 B, P to the negative 1 to the negative 1. Finally, suppose that A is similar to B and B similar to C. Then there exist invertible matrices P and Q such that PA P to the negative 1 equals B and QB Q to the negative 1 equals C. Since C equals QB Q to the negative 1 equals QPA P to the negative 1 Q to the negative 1 equals QPA QP to the negative 1, the relation is transitive since the composition of invertible matrices is invertible. Two matrices that are equivalent in this manner are said to be similar. Oh gosh, okay. I'm gonna need another drink of Diet Coke. A partition P of a set X is a collection of X1, X2 non-empty sets such that each individual they are pairwise disjoint. So if you have two sets in your partition, they will not have any overlapping elements, and the union of all elements in all the sets equals the original set X. Let sim be an equivalence relation on set X and let X be in X. Then we define by closure of X to be the set of all Y in X such that Y is similar to X, and we call it the equivalence class of X. We will see that an equivalence relation gives rise to a partition via equivalence classes. As well, whenever a partition of a set exists, there is some natural underlying equivalence relation, as the following theorem demonstrates. Theorem 1.25. Given an equivalence relation sim on a set X, the equivalence classes of X form a partition of X. Conversely, if P equals Xi is a partition of a set X, then there is a equivalence relation on X with equivalence classes Xi. This is one of the fundamental forms of proof we're going to have. We have these two separate objects, equivalence classes and partitions. And what we're showing is that these two different objects are really describing the same phenomenon, just in different interpretations and different notations. Proof. Suppose there exists an equivalence relation sim on the set X. For any X in X, the reflexive property shows that X is in X, and so the equivalence class of X is non-empty. Clearly as well, since X is in each individual X, the union of these equivalence classes is our original set X. Now, let X and Y be X. We need to show that the equivalence class of X is equal to the equivalence class of Y, or the equivalence class of X cap the equivalence class of Y equals the empty set. Suppose that the intersection of X and Y, their equivalence classes, is non-empty, and that Z is in their in-between equivalence class. Then Z is similar to X and Z is similar to Y. By symmetry and transitivity, X is similar to Y. Hence, X is a subset of Y. Similarly, Y is a subset of X, and so X is equal to Y. Therefore, any two equivalent classes are either disjoint or exactly the same, which is the condition for a set to be a partition or a collection of subsets. Conversely, suppose that P is equal to Xi is a partition of a set X. Let two elements be equivalent if they are in the same partition. Clearly, the relation is reflexive. If X is in the same partition as Y, then Y is in the same partition as X. So if X is similar to Y, implies Y is similar to X. Finally, if X is in the same partition as Y, and Y is in the same partition as Z, then X must be in the same partition as Z, and transitivity holds. Corollary. Two equivalence classes of an equivalence relation are either disjoint or they are equal. Let us examine some of the partitions given by equivalence classes in the last set of examples. Example 1.27. In the equivalence relation example 1.21, which as a reminder was the set for all, the rule is actually, the set of all rational numbers that are that are actually equivalent when you evaluate them numerically. Two pairs of integers p and q and r of s are in the same equivalence class when they reduce to the same fraction in its lowest terms. Example 1.28, the case with differentiable functions. In the equivalence relation example 1.22, two functions f of x and g of x are in the same partition when they differ by a constant. Example 1.29. We defined an equivalence class on R squared by x1, y1 is similar to x2, y2 if x1 squared plus y1 squared equals x2 squared plus y2 squared. Two pairs of real numbers are in the same partition when they lie on the same circle about the origin. Since when they lie on the same circle, this will be an invariant value. Example 1.30. Let r and s be two integers, and suppose that n is an n. We say that r is congruent to s modulo n, or r is equivalent to s mod n if r minus s is evenly divisible by n. That is, r minus s equals nk for some k and z. In this case, we write r is congruent to s mod n. For example, 41 is congruent to 17 mod 8. Since 41 minus 17 equals 24 is divisible by 8. We claim that congruence modulo n forms an equivalence relation of z. Certainly, any integer r is equivalent to itself, since r minus r is equal to 0, and is as such divisible by n, trivially. We now show that the relation is symmetric. If r is equivalent to s mod n, then r minus s is equal to negative s minus r is divisible by n. So, s minus r is divisible by n, and s is equivalent to r mod n. Now, suppose that r is equivalent to s mod n, and s is equivalent to t mod n. Then, there exist integers k and l such that r minus s equals kn, and s minus t equals ln. To show transitivity, it is necessary to prove that r minus t is divisible by n. However, r minus t equals r minus s plus s minus t equals kn plus ln equals k plus l of n. So r minus t is divisible by n. If we consider the equivalence relation established by the integers modulo 3, then we have the sets in all integers mod 0 mod 3, all integers 1 mod 3, and all integers 2 mod 3. Notice that 0 union 1 union 2 equals z, and also that the sets are disjoint. The sets 0, 1, and 2 form a partition of the integers. The integers modulo n are a very important example in the study of abstract algebra, and will be quite useful in our investigation of various algebraic structures, such as groups and rings. In our discussion of the integers modulo n, we actually assumed a result known as the division algorithm, which will be stated and proved in Chapter 2. Sage is not for us. Excuse me. Oh my gosh. So we'll begin the questions. I'm just going to take a intermission to run to the restroom and grab a mission. Grabbing coffee. Smile. Okay. Let me quick edit some stream stuff. Before we do the problems, it's page 25. I feel like it is only fair to put the name of the book and the authors in there, because they put a lot of, like, in the stream title, because they put a lot of effort into this. I don't want to devalue that. Let me double check. Who was exactly the authors of this? Algebra theory applications. Because the way the title is put, I want to make sure. I don't know what the university is properly called. Tom. So does Tom Jensen. What is algebra theory and applications? Combined Tom Jensen. Done. Let's check the page. We're going to page 25. Okay. Reading questions. What do relations and mappings have in common? A mapping, in this case, I'll just answer this because it doesn't look like anyone's in chat right now, so I'll just keep this for the VOD. A mapping is in itself a relation that assigns to each input a unique output. What makes relations and mapping different? Relations can either fail to have outputs on a part of your input, or can have multiple outputs per input. State carefully the three defining properties of an equivalence relation. In other words, do not just name the properties, give their definitions. First is reflexivity, which is saying that for every element in the set that you have an equivalence relation over, you have an identity in your relation. X is equivalent to X. It is the statement about the existence of something. The next two are relational. Pun not intended. Symmetry is that if X is equivalent to Y, then Y is equivalent to X. Equivalence goes both ways. Third is transitivity. If X is equivalent to Y and Y is equivalent to Z, then, well, you can just swap out that Y for Z and get that X equivalent to Z. What is the big deal about equivalence relations? They provide a nice way to partition sets into other sets based on some sort of ruling that is fairly easy to describe, even if, as we'll see in the cases of integers modulo something, they have very complicated behavior emerging from that. Describe a general technique for proving that two sets are equal. Well, we define two sets to be equal and they have the same elements, and to have the same elements means that both one set is a subset of the other, and that set is then a subset of your original set. Now, suppose that we have A, B, and C is equal to that. Then we wants us to describe this. So, A cap B is the set of all X is a even prime. which is literally just equal to the set 2. The only even prime is 2, because we're also considering positive numbers. Describe B cap C. C. B is defined to be primeness, okay. Equals, it's prime and multiple of 5. Well, if anything is above a multiple of 1 times 5, then by definition it will be the multiple of something ultimately that is a prime with other primes and 5, so it's not prime. So we know that only the case of 1 might work. We know that 1 times 5 is itself a prime, so we know that this set is equal to 5. A union B equals the set that either X is even or X is prime, which is equal to, I'll be using notation here, 2 times Z, which is a set of all integers, times 2, times the primes, we might call them P. There's not a well-defined way to write this, because at most we can describe the non-prime elements that are not in this set as the sets of L elements with prime factorization, not including 2. A cap. God, I need to expand the space on this whiteboard. Alright. A cap B union C is the set of all X is even and either X is prime or X is a multiple of 5. So, in the first case, if X is even and X is prime, we know that's just going to be equal to 2. The other case, that X is even and X is a multiple of 5, means that we have the set of all multiples of 2 times n times 5. Which we can just simplify, because like 2n, this will describe all even numbers as we range over n. So we can just simplify this to being 2 union with 10 times n. Okay. Wow, I'm already being hit in chat by bots. It looks like impressive. Alright, what's the next problem? If A is equal to A, B, and C, and B is equal to 1, 2, and 3, with C equal to just the singleton set X and D equals the empty set, list all the elements in each of the following sets. Oh my gosh, okay. There are a lot of exercises here. I'm probably not going to get them all because, oh my god, okay. Alright, first of all, A times B, we'll define it individually for this case. A B equals the set of all, we're not going to actually include the set of all, because that's going to take up space, and on this whiteboard, space is limited. So we have A1, A2, 3, B of 1, B of 2, B of 3, C of 1, C2, C of 3, I just finished doing something. Alright, so now we need B. We need B times A. Now notice for B times A that we simply have it flipped around. It'll be 1A, 1B, 1C. I'm just going to put dots here for simplicity. Note that it's the same thing, but every input, for example, these two inputs are just flipped around. Now, next they want us to show A times B times C, which in this case is going to be nice, because C is only one element, so what every element will be, it'll be some element from our list. And then we will simply include an extra x, because this is the only element that C has. So we have B1, x, C1, x, blah blah blah. And I'll just quick write the dots down here, save on space. The important thing to note is that A times D is the empty set, so just simply the empty set. Alright, find a example of two non-empty sets A and B for which A times B equals B times A is true. Well, let's think about what it would mean for A times B to be equal to B times A. This means that A, B is in A times B implies that B A in A times B. But realize that this just means, literally, that A is in A cap B and B is in B cap A. Now, this entire thing, this is literally just an arbitrary element we chose. So A cap B must be our entire input domain A. However, the only way for A to be equal to A cap B is for A to be a subset of B. And doing a similar logic, we get B is a subset of A, which implies that A is actually just equal to B. In fact, this is a bit more than they wanted to show. This is a way of saying that we have the case that A times A equals A times A. And this will be the only case where such a statement holds. If anything else, if there is any deviation between the two sets, there will be an asymmetry in the product. Oh gosh, Paint, why do you do this? I know I am relying on MS Paint for a Twitch stream. It's slightly embarrassing, but please don't do this. Okay. Prove A union is empty set equals, okay. Suppose that X is in A union empty set. This means that either X is in A or X is in empty set. By definition, X cannot be in the empty set. The empty set is empty. That's what makes it so. So X can't be that, which means that X is in A union empty set implies that X is in A, which means that A union empty set is a subset of A. Also, I'm just using this common like the bar under for the subset symbol. And doing a similar argument will show you that X is a valid element of A union B. So A is a subset of A union empty set. So A union empty set equals A. Prove A union B equals B union A and A. Okay, I think I'll do a few more of these prove statements here, because eventually it just gets kind of silly, to watch a video of someone proving all these. But okay, first of all, okay, also A cap empty set. Suppose that X is in this. This implies that X is in A, and I'll put in massive letters here. X is an empty set, but X is not in the empty set. A contradiction. Now, since we have a contradiction, that means our premise, our assumption that this was true must be wrong. So X cannot be in the intersection. But notice that this was for any arbitrary element X. It doesn't matter what we picked here. No element could exist in here, which means by definition, this is the empty set. Oh gosh, I'm gonna clean up this, otherwise it's gonna annoy me to no end. Okay. Prove commutativity. Actually, okay, for 5, I will trust that you guys know what to do if you're watching this, by simply doing another OR argument, like A is in A union B, assume it's in A, then it's in B union A. By definition, that's likewise, and likewise for capping. The last thing I will prove is the distributive property of sets. It's kind of useful, but it's not really. So I'm gonna be lazy and not prove that. Prove A is a subset of B if and only if A cap B equals A. So first, we assume this is true, and we try to prove this first. So suppose we have some X in A, which is a subset of B. Then X is in B, so X is in A, B. So A is a subset of A cap B. Now to prove that A cap B is a subset or equal to A, suppose X in A and B. Oh, well then trivially, A cap B is a subset of A, is a subset of A cap B, which implies equality. Now, this is just the first part of what we have to prove, right? Next, we have to prove what it means to prove the if and only if, is that if this is true, then this is true. So we let X in A. Then, by equality, X is in A cap B, which implies that X is in B, which by definition means that A is a subset of B, since we showed this for any arbitrary X in A. All right. I feel like they're like. Don't really feel like there's anything big to prove here. Okay. Which of the following relations? So yeah, we'll just skip ahead a little bit. Which of the following relations, f from the rational numbers to the rational numbers, define a mapping? In each case, supply a reason why f is or is not a mapping. So suppose that we define f of p over q to be equal to p plus 1 over q plus 1. Oh, well, not q plus 1. Is that correct? Let me actually double check it. P minus 2. Now, what this is really asking is if we alter this, if we say that f of, like, is f of n p over n q equal to f of p over q? Because remember, we can, by rational numbers, cancel out this n in our final thing, so we should be able, that should be reflecting this. So suppose we have np plus 1 over np minus 2 equals p plus 1 over p minus 2. Multiplying gets us np squared. Well, actually, yeah, before I factor this out, before I make a fool out of myself and the fact that I can't multiply numbers, p minus 2, p plus 1, and p. So we get p squared minus 2np plus p minus 2 equals p squared minus 2p plus np minus 2. So let's take this out, move this up. So we are able to cancel out this from both sides. This is minus 2. We can cancel this from both sides. And we ultimately get negative 2np equals to negative 2p plus np. So we can multiply this to get 3, no, not 3p, why was about that? 2p plus np equals 0. So we factor that out to simply get 2 plus n equals 0 if p is not equal to 0. So we see that this is not well defined because there are values of n such that this statement isn't true. This statement isn't true for 2, 3, 5. It's equal for negative 2, which might just be a consequence of me doing the math wrong because it's very possible. It's also possible that this function does equivalent, like, show a symmetry in the negative 2 case, but like, let's not worry about that right now. But ultimately what this means is that ultimately, no, this does not hold true because because we are running into a contradiction from an assumption. That means that our assumption must have been wrong, so they're not equal. Okay. Okay. Yeah, because the rest of this is very tiring for B. Because it's P over Q, we have that if we multiply both P and Q by N, we get a statement which is ultimately still true. And it's going to cancel out on both sides. For f of P over Q equals P plus Q over Q squared, notice that if we multiply Q by N, we get N squared in the denominator, but NP plus NQ equals NP plus Q. So we're going to have an extra factor of 1 over N at the bottom. It's going to mess with the theory for the case that N is not equal to 1. And for that final case, D, that holds true because for each individual summoned, P and the N, if we multiply P and Q by N, will be scaled by the same factor. And we're dividing it in both the numerator and denominator, so it's still a well-defined function. Okay. Determine which of the following functions are one-to-one and which are onto. If the function is not onto, determine its range. Okay. E to the x is, I'm going to just like run through this, assume you know this. E to the x is strictly increasing, which because it's strictly increasing and defined for all real numbers, it is one-to-one. It is not onto. It will never hit 0 to negative infinity inclusive. Alright, for B. N squared plus 3. Well, by just simple properties of quadratic functions, we're going to have a non-injective function. N is going to be equal to negative n, for example, on this, or x is going to be equal to f of x is going to be equal to negative f of negative x. And it will be the range from 0 to infinity. For sine of x, it will be neither injective nor surjective, because it is a periodic function, a bounded continuous periodic function. F of x equals x squared is once again going to be not injective, not surjective. Alright, 19. Let f of a to b and g of b to c be invertible mappings. That is, mappings such that, okay, give me a second. F of negative 1, g to negative 1 exist. Show that g circle f negative 1 equals f of the negative 1 circle g. Alright, this is actually a really good problem. So, g circle f of negative 1 composed with h. So we get that g composed with. So, okay, for this, let's use our defining factor to set up. So we know that g circle f negative 1 circle f circle g equals f to the negative 1 is going to be equal to ID. Right? So we have this. So what we do is we first take this and we drop the parentheses and we multiply this on the right side by g to the negative 1. These will cancel, which will get us g circle f to the negative 1 circle f equals g to the negative 1. I was so dumb. Wait, give me a second. I actually did something dumb and messed up the order of it because I'm far too tired. This is why you gotta really double check the details of proofs. If you just went along with what I did and weren't screaming at me, watch this. So when I was doing this, I was being dumb. What we should instead be defining is g circle f equals ID by what it literally is. So we get, using a simple line of logic, g circle f to the negative 1, circle g circle f circle f to the negative 1 equals f to the negative 1. These two cancel out, so we get g circle f to the negative 1 circle g circle g to the negative 1 equals f to the negative 1 circle g to the negative 1. These cancel out, which just ultimately leaves us with g circle f to the negative 1 equals f to the negative 1 equals g to the negative 1. An important thing to notice here that you may take for granted now, you will not later, is that we are reversing the order of composition here. Initially we have f going to g, but now we have g going to f. And it's inverse, which, just trust me, it's going to be extremely important, especially if like category theoretic relations to this. Alright. 20. Define a function f from n to n that is 1 to 1 but not onto. So we can simply define this to be f of x equals 2x. We're going to hit all the even integer count, the even whole numbers. We're not going to hit the all whole numbers. Now, define a function f from n to n that is onto, but not 1 to 1. So we define f of x to be equal to the floor of x plus 1. Actually, wait. Let me alter it. The floor of x over 2 plus 1. If you notice, this will be a function that goes 0, 0, 1, 1, 2, 2, 3, 3. Or no, in this case it will be 0, 1, 1, 2, 2, 3, 3, 4, 4. And that additional 1 will make it always above 1. And obviously this hits every integer, just does it in a discrete stepwise manner that takes a while. And this addition makes sure it's in the domain, so we have a function that is like truly onto but not 1 to 1 for the real numbers. Prove the relation on R squared by x1 and y1 similar to x2 y2 if x1 squared plus y1 squared equals x2 squared plus y2 squared is an equivalent relation. No, we'll worry about that later. Ultimately, with that, it is literally just the fact that these statements are equalities of each other, and this is already an equivalence relation. You can more so think of this as like, if we have symbols that we do something with to these symbols, and they're equivalent, and like, they're already going to be under that equivalence relation, it's just going to be another thing, except we put fancy notation around it. Alright, man, okay. This I'm far too lazy to do. F made a B and G of A, B, B, C, B maps, G both 1 to 1, just G of F 1 to 1, G of F on 2. For this, I will show that if F and G are both 1 to 1, then G composed with F is 1 to 1. So suppose f g are 1, 2, 1, then g goes to f a1 if gf is f of a2. Then we have, because g is 1, 2, 1, f of a1 equals f of a2. And because f is 1, 2, 1, a1 equals a2. The other properties are proved in a likewise manner. Define a function of real numbers, it's just a rational function. I'm extraordinarily lazy. Ooh, okay. Oh, this is useful for topology, but at the same time. Okay, I'll prove. For this, it should be the obvious why the image of a union is the union of images. But the intersection case is more subtle. So, f of, suppose f y is in f of a1 cap a2. Then there is some x in a1 cap a2 such that x equals y, meaning a1 and f of I is in f of a2. So y is in f of a1 cap f of a2. Now, the important thing here is showing the case where equality fails. So let's write a fake proof, shall we? Let's try to, first of all, pretend we didn't know better. And we try to prove that y is in f of a1 cap f of a2. Implies that f is in a1 cap a2. Let's write a false proof. So, because this, we know there exists x in a1. This simple just means there exists an x in a1. And y, or I should say x1 a1, x2 in a2, such that 1 f of x2 equals y. However, at this point, realize we're stuck. With our assumptions, we can't assume that a1 is an a2. So let's try to construct a counterexample. We need some function f such that there are two ranges. So we need from x to y. And we need two subsets, a1 A2. From our previous example, we know that A1 and we need to basically show that, okay. We need some A1, A2 subsets of X with AX1 in A1 set minus A2, X2 in A2 set minus A1, and f of x1 equals f of x2. Now note that it's actually really simple to do this. Just let x be the set literally of just two symbols, but we're going to just put in this case 0, 1. Let y literally just be a set including a single element. And let f from x to y be constant. Then, if we let a1 equal 0, a2 equal 1, then it's easy to see that their intersection is the empty set, but they both map to the same thing. Like, we still have an element in this, but we don't have an element in this for this case, which means that the theorem we were trying to prove is false. So equality is not actually strict in this case. If we have these cases along with this, then it fails. Determine whether or not the following relations are equivalence relations in the given set. If it's a equivalence relation, yeah, okay, so these are kind of just like very boring. 28 is what I've been saying. The error in the line of reasoning is that the symmetric and transitive properties is like, they are something about things that already exist. Like, if we already know that x is similar to y and y is similar to x, then yeah, that works. But if we don't know necessarily that any elements exist, well, we still need that axiom, that reflexive property, to show that there's things in there in the first place. Alright, projective realigned. This is the last thing I'm going to do because it's last exercise. It's going to be a good place to stop for today. And the projective realigned is a very useful example in many cases. Define a relation r squared on r squared. Define a relation r squared except for the point 0, 0, but letting x1, y1 similar to x2, y2 if there exists a non-zero real number, lambda, such that x1, y1 equals lambda x2, lambda y2. Prove that lambda defines an equivalence relation r squared. Okay, so I will do a really cool thing. So we first of all say x1, y1 similar to if there exists a lambda greater than 0 with x1 lambda x2 y1 y2. So first of all, raffle. So x1 y1 equals 1 times x1 1 times y2. So lambda in this case equals 1. We good. Symmetry. Suppose that x1 y1 equal lambda x2 lambda y2. Well, we have vectors, and because of how we define like vectors and the fact this is not 0, we have that 1 over lambda x1 y1 1 over lambda y1 equals x2 y2, which checks out symmetry. And for transitivity, we have that x1 y1 equals lambda x2 lambda y2 equals gamma gamma lambda x2 gamma lambda x3. Okay, I did kind of put the cart before the horse, but it's easy to show that anything will be an expression by this by just substituting in. So just let lambda prime equal gamma lambda, and we good. The projective line equivalence is a equivalence relation. Now what is this? Let's think about this. I'm going to sketch out a geometric argument. There are purely topological arguments, but they can be kind of painful. So, suppose we have like the Cartesian coordinates. Now, suppose we have some point here. The entire line passing through that point, along with the point in the negative direction, this line is identified as all equivalent points, which means that we can think of the projective plane, the equivalence classes, as being represented in a sense by this angle, or this kind of way that we take, the way we take a circle, because if we only have to worry about points in the circle, and gluing these ends of the circle all together continuously along it. Famously, it is not a very nice procedure to take this object and like try to glue these ends together in a very forceful way. For this case, you just be collapsing down like these points, and you'd kind of be like wrapping into a half circle in a sense, where these points are identified, but otherwise you would give a unique line by each angle in here. But yeah, that'll be another time, I guess. Thanks for tuning in. Have